just like with velocity vectors, a combined force vector can occur when there are several different forces contributing to the situation. So, in a case like that, we say that the resultant force vector is the sum of all of the contributing forces. In the special case where there's no motion whatsoever as a result of all the forces, we say that our system is in equilibrium, and the sum of all the force vectors is actually 0. All right, we'll look at a couple of examples. In example 12, we have 2 ropes attached to a sled, each being pulled by a different person. Kim pulls 5 degrees west of due north, force of 35 pounds, and Kate pulls 12 degrees east of due north, with a force of 20 pounds. Find the resultant force vector and the magnitude and direction of that resultant force. So let's see what we've got. Kim pulls 5 degrees west of due north, so just slightly to the west here. With a force of 35 pounds. Call that F for Kim. And I could easily write down that vector. Let's see, I do need to take into account that that 5 degrees is not from the positive x-axis. That would have to be 95 degrees with the positive x-axis. So I'm going to go with 35 cos 95 and 35 sine 95. Or approximately negative 3.05 and 34.87. Seems reasonable. Second quadrant vector. Everything matches up. All right, what about Kate? 35 pounds, 12 degrees east of due north. Excuse me, 20 pounds, 12 degrees east of due north. So let's see, east of north, that would mean that this is 12 degrees, and the magnitude is 20 pounds. Again, I want to make sure that I think of my angle with respect to the positive x-axis. So instead of 12 degrees there, I'm going to think of it as the complement, which would be 78 degrees from the positive x-axis. So for Kate, we will go with 20 cosine 78 degrees and 20 sine 78 degrees. Or approximately 4.16 and 19.56. So my resultant force vector, Fr, is just going to be the sum of Kim's force and Kate's force. Which is going to give me 1.11 and 54.43. The resultant vector. Notice that that is just slightly to the east of north, right? This is a first quadrant vector. So it turns out that they're going to go just slightly to the east of north in their final result. In fact, we'll figure out the angle momentarily. Let's go ahead then and get magnitude and direction. So the magnitude of the resultant force is about 54.44. And let's see here, that would be in pounds. And the direction of the resultant force, let's just draw it here. It's 1.11 in the x direction and 54.43 in the y direction. So I'm going to say that the tangent of theta is f2 over f1, would be 54.43 over 1.11. And I'll use the inverse tangent in order to get my theta. And I get about 88.8 degrees. So this angle here with the positive x-axis is 88.8 degrees. Since everything was described in the original problem, I am so sorry, you guys. I did not push that up. Let me bring that up for you so you can see that. So all I did was sketch my vector, and there's the tangent of theta is f2 over f1. Inverse tangent gave me that 88.8 degrees. All right, since everything in the original problem was described with respect to due north, we could also say, well, we could easily get this angle in here, right? Just subtracting from 90 degrees would give me what? 1.2 degrees? And so my angle could be described as 1.2 degrees east of due north. And then it's just kind of similar to the way the original problem was described. All right. In example 13, we have a three-way tug of war. One person exerts the force F1, second person has got a force of F2. We'd like to know what force must be exerted by a third person in order for the object at the center to remain motionless. And then we'll find the magnitude of that force. Motionless tells me that I am in equilibrium. Meaning that the resultant force must be zero. So, zero is the sum of all three forces. I know F1 and F2, so in fact if I went ahead and just did my subtraction ahead of time, notice that F3 would be minus F1 minus F2. Which would be -8, +3, -1. It's just the opposite of F1. And the opposite of F2 would be +2, 0 for the J, and -2 for the K. So -6, 3, -3 is going to be my resultant, or not my resultant, rather my F3, that will be needed to balance out F1 and F2 and give us no motion, and the magnitude of F3. Is going to be approximately 7.35. And I guess they actually didn't give us a unit here, so 7.35 newtons or pounds or whatever our force units happen to be. All right, in example 14, a large retail store hangs signs from the ceiling identifying the different sections of the store. Each sign weighs 25 pounds and is suspended from two identical chains that make 40-degree angles with the ceiling. Find the magnitude of the force also called the tension in each chain. All right, so let's sketch this situation. We've got the ceiling, and then we've got the sign, which I'm just going to represent as a point hanging from the ceiling. And here's the two chains. And these are 40-degree angles. We know that the force of gravity is going to pull down on this object, on this sign. So this is my FG, force of gravity. All right, I need to decide where to put my axes in this situation. And I'm simply going to choose to make the center here the sign. That's going to be my origin. And so I'm going to end up with axes that look like this. That way I've got my FG starting at the origin. It's in standard position already, which is an advantage to me. And I also can say that the tension vectors have to pull back up, otherwise the sign would fall, right? So this can be tension vector 1, and this one can be tension vector 2. Now I do know that the sum of all three of these force vectors must be 0, otherwise the sign would be moving. It would either be pulled up into the ceiling or fall down to the floor, none of which, of course, should be happening. So we know that FR, which is going to be the sum of T1 plus T2 plus FG, must be 0. This sign is in equilibrium. All right, let's get some values for those various vectors. We'll start here with FG. We certainly know that the sign is 25 pounds, so the force of gravity is pulling downward with a magnitude of 25. So FG must be 0, negative 25. As far as the tension vectors, we have a little bit of geometry to do here. By the alternate interior angle theorem, if that's a 40-degree angle, this is also a 40-degree angle. And I also don't know the magnitude of that vector, so let me just call it capital T for now. Excuse me. And I'm going to say that T1 is therefore T cos 40 degrees and T sine 40 degrees. As far as T2, by the symmetry of the situation, the magnitudes of these two vectors are going to be the same. So if this vector has a magnitude of T, this one does as well. Now this angle would be 40 degrees, meaning that the angle with the positive x-axis all the way around to here would actually be 140 degrees. So for T2, I'm going to go with T cos 140, T sine 140. All right. I'm going to plug all of that into my equation. And as I do so, I'm going to actually use some decimal values for these. In fact, maybe I should just do that down here. Let's go with some approximations here. The cosine of 40 degrees is 0.766. So this is 0.766t. And the sine of 40 degrees is 0.643. So 0.643t. Cosine of 140 is negative 0.766. And that is multiplied by t. And the sine 40 is 0.643. So if I take these three vectors and state that they must add up to 0, I would have 0.766t 0.643t for t1 plus negative 0.766t, 0.643t for t2 plus 0, negative 25 must all equal 0, 0. You'll notice that the x values already add up to 0, but the y values, that's going to give me what? 1.286t minus 25. So the x component is fine. It's the y component that's going to give me the answer. Since 1.286t minus 25 must equal 0, 25 divided by 0.1268, 286, excuse me, is 19.44. And so the tension in each chain has a magnitude of 19.44. Notice T was the magnitude of each tension vector. And that would be in pounds. All right, we're going to do one more problem very similar to this, but we're going to take a similar problem in 3 dimensions as our last example in this section. All right, so I like to call this one the Phantom of the Opera problem. If you've ever seen that show, you know that it starts with a large chandelier almost falling on the audience. And we're going to look at a theater set with a large chandelier weighing 500 pounds. And it's got to be suspended from the ceiling with the top 4 feet below ceiling level. Workers anchor 4 cables in the ceiling, as shown in this diagram. Each cable is rated to 150 pounds. Will the cables safely support the chandelier? So what we'll need to do is figure out the tension in each cable, and hopefully the tensions aren't any more than 150, and we'll have a safe chandelier. All right, so we've got our picture here, and I'm going to start by saying we know that the chandelier weighs 500 pounds, so for sure the downward pull, force of gravity, has a magnitude of 500. That means that Fg can be written as 0, 0, negative 500. All right, there are 4 tension vectors, and the book that I actually stole this problem out of has these pulling down, but in fact, the tension vectors really need to pull up to work against this. So I'm not in love with this diagram. I'm going to redraw these tension vectors, pulling upward against the force of gravity. And to get each tension vector, I'm going to go ahead and find a unit vector in the correct direction, and then I'll multiply by the magnitude of the tension. Now remember that the magnitude of the tension is what we don't know yet. Once again, if you look at the anchor points, they're perfectly symmetric around the origin. Therefore, the tension in each cable is going to be identical. So I'm just going to again use capital T to represent the magnitude of each one of those vectors. So let's call this one F1. I'm going to first of all say let's get a unit vector in the correct direction, and then we'll multiply it by the tension. So my unit vector, I'll take this actual vector, which I can get just taking terminal minus initial. That would be 0, 2, positive 4. I'll divide it by its magnitude. The square root of 0 plus 2 squared is 4, and 4 squared is 16. So there's a unit vector in the correct direction. And then I'll just multiply that by capital T. Let's do the same for F2. F3, and F4. Tension is going to be T again, times the unit vector in this direction. Take terminal minus initial. This time that's going to give me negative 2, 0, 4. And notice that the denominator is going to be the same, right? Square root of 4 plus 0 plus 16 is just the square root of 20. All right, F3. Magnitude of T times the unit vector in this direction, which would be 0, negative 2, 0. Oh, I'm sorry, 0, negative 2, 4. Same magnitude, 0 plus 4 plus 16 gives me the square root of 20 again. And then finally F4, once again I need the magnitude of T times the unit vector in the correct direction. Subtracting terminal minus initial, 2, 0, 4. And the same magnitude, square root 20. All right, when I add up all 5 of these vectors, because the chandelier is not moving, hopefully, we want to result into 0. Equilibrium, right? Let's see if we can do a little mental arithmetic here. The denominator on all of these is the same, right? That's really the square root of 20 as well. And so if you look at the x values, I have 0 and 0, negative 2, 0, and positive 2. Those all add up to 0. And I think the same thing is going to be true for y. We got 0, 2, 0, negative 2, 0. Those all add up to 0 as well. The interesting part is going to be what happens in the z component. I have a negative 500, and then all of these are multiplied by t, and they're all 4 over the square root of 20. So I'd have 4, 8, 12, 16 over the square root of 20 times t. It's that last component that gives me the equation that's helpful. Since this has to be equal to 0, I could bring the 500 over. So 500 equals 16 over the square root of 20 times t. And t is going to be 500 square root 20 over 16, which is about 139.75. Our forces were in pounds, so the tension in each cable is just a bit under 140 pounds, since the cables are rated to 150 pounds. That means yes, the cables will safely support the chandelier. All right, that brings us to the end of section 11.1 and 11.2C.